Objective 2.2, Identifying and Evaluating Polynomial Functions. In this lesson, we want to be able to identify when a function is a polynomial function, and we want to be able to evaluate polynomial functions for given values using direct substitution and synthetic substitution. So again, let's start with a little bit of vocabulary. First of all, what is a polynomial function? So according to this definition, it says a polynomial function has the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus blah 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 plus a sub 1 x plus a sub 0. What the heck does that mean? It's an ugly form of a polynomial, but it's what they have to do to be able to generalize what a polynomial looks like. Okay, but let's break this down a little bit. Basically what they're saying is you're going to have this leading term, and that term is going to have some degree to it, some exponent. Okay, so whatever that exponent is, the coefficient, which is what a sub n represents, all of these a's represent coefficients. And so in order to keep them all the same letter, but still make them different, we use subscripts. So that subscript of n is going to match with whatever our exponent is on x. Okay? Now, polynomials can be various different degrees. And so in order to show what's going on in a general form, we're saying, okay, so here's my n, and then the next term is going to be one less. So my n minus 1 here, and then my subscript of n minus 1 there on my coefficient. Okay? And it just keeps going and going and going until we get down to here where we just have an x term, which means technically my exponent is 1, therefore my subscript on a will be 1. And then finally I get down here to a sub 0. Notice there's no x in this term. So technically that means it must have been x to the 0 power, which means it would be equal to 1, which means I don't really need to write it there. I just keep whatever the a sub 0 was. And this is what we call the constant term because there's no x value in it. Okay? So even though this is kind of ugly, it is the general way to represent what a polynomial would look like. Okay, now if we continue with this definition, it goes on to say that a sub n cannot equal 0. So that's just saying that we can't call this an x to the 5th polynomial if it's a 0 in front of it, because we wouldn't really have the x to the 5th term. Okay, that's all that means. And the exponents are all whole numbers. Okay, so all of our exponents have to be whole numbers. And then it gets a little bit more specific by saying that a sub n is called a leading coefficient. So that's this one out here. Since this is a leading term, the coefficient is called the leading coefficient. A sub 0, we already mentioned a minute ago, right here, is what's called our constant term. And whatever n is, whatever the highest exponent is, we call that the degree of the polynomial. Okay? So lots of bits and pieces there that we need to keep in mind as we move forward. We also want to know that polynomial function is considered to be in standard form if the terms are written in descending order of exponents from left to right. So we always want our biggest exponent to be the first term, and then write them in order with descending exponents until we get down to the constant on the far right. Then we have synthetic substitution. This is another method for evaluating a polynomial function, which is equivalent to evaluating the polynomial in nested form. We'll see what that means in one of our examples. And then this vocabulary also includes the term end behavior. End behavior is something we're going to talk about in a future lesson, and so we're not going to spend time on it right now. We'll talk about it when we get to it with graphing. All right, so first of all, types of polynomial functions. Polynomial functions have certain names to them depending on what degree they are. And you need to be familiar with these names, because if they get used in a lesson or if they get mentioned in directions, you need to know what they're talking about. So let's just take a minute to look at this. If we have a function, a polynomial, that has a degree of 0, then that means we just have f of x equal to some number, like maybe f of x equals 3. Okay, that is called a constant function. Okay, it's a degree of 0. That means there's no actual x in the function itself. It's just f of x equals a number. That's called a constant function. If we have a degree of 1, then we have basically what ends up looking like slope-intercept form. They're just writing it differently with the a's to fit the polynomial form. Okay, but this we're very familiar with at this point. This is a linear function. If we have a degree of 2, that's what we were working on last chapter, then we're dealing with quadratics. So you see here we've got a 2 for our biggest exponent, and our leading coefficient here is represented by a sub 2. A cubic means we have a degree of 3, so 3 is going to be our highest exponent. And a quartic has a degree of 4, so 4 will be our highest exponent. So you need to be familiar with these names, and you need to understand what degree of polynomial they're referring to so that you know what the problem's talking about. The other thing that I want to point out here is for you to realize that all of these are types of polynomials. So even when it is just f of x equals a number, it's still a type of polynomial. Even our linears and our quadratics are all types of polynomials. They all fit the definition of what a polynomial should be. Yep. I'm gonna have to do this quick because I'm almost out of battery, so let's keep moving. There we go. Okay, so here's an example. We want to decide whether the function is a polynomial function. If it is, write the function in standard form and state its degree, type, and leading coefficient. So in the first case, we have f of x equals 3x to the 1/2 minus 2x squared plus 5. This one is not a polynomial function because of that 1/2 exponent. In our definition, it said all of the exponents had to be whole numbers, and so this would not be a polynomial. Now, how about f of x equals 3? Well, we were just looking at that one. It is a polynomial function. It's already in standard form because there's only one term. It has a degree of 0 since there's no x in it, and therefore that makes it a constant function. And that 3 would be considered the leading coefficient. In the next function, what do you think about that one? Is that polynomial? The answer is yes. It is a polynomial function. The standard form would be negative x plus the square root of 5. It has a degree of 1, so that makes it linear. And the leading coefficient is a negative 1 in front of our x. The square root of 5 as our constant does not make it a non-polynomial. We can have any kind of real numbers for the coefficients and constants. Square root of 5 is a real number. It's a polynomial. All right, why don't you try a few quick? We've got 3 functions here. Do the same thing. First decide if it's a polynomial, and if it is, then write the function in standard form and state the degree, the type, and the leading coefficient. Don't forget to answer the question on Zaption before you continue, and then you can come back and we'll continue with example 2. All right, so here are your answers. F of x is a polynomial function. The standard form would be 5x cubed plus x. That means it's a degree of 3, which makes it cubic, and the leading coefficient, that's what LC stands for, is 5. The second one is also polynomial. Even though it's a pi there in front of x to the 4th, that doesn't change the fact that everything still fits the definition. So we would actually write this as pi x to the 4th minus 4x plus 6. That makes it a degree of 4, so it's quartic, and the leading coefficient would be pi. In our third function, we do not have a polynomial because we have that negative 2 as an exponent, and exponents can only be whole numbers. So our third function is not polynomial. All right, now for evaluating polynomial functions. When you evaluate, you are putting a value in for x. So we're given this function f of x equals 4x to the 4th plus 2x cubed minus x plus 7, and we want to evaluate it for when x is equal to negative 2. So there's 2 ways you can do this. What they referred to as the nested method in the directions is also called direct substitution, and it simply means you're going to put negative 2 in for x in the function and work it out. So that means our first term is going to be negative 2 to the 4th times 4, which gives us 64. Our second term is going to be negative 2 cubed, and then times 2, which gives us negative 16. Then we're going to take minus negative 2, which will be plus 2, and then our constant of plus 7. So if we put all of that together, we end up with an answer of 57. Now, that's not a terrible way to do it, but it can get a bit complicated depending on how big our polynomial is. So we also have a second method, which is called synthetic substitution. And in synthetic substitution, we are going to use the coefficients of each term and line them up. But notice we have this 0 here. This 0 is because we're missing an x squared term. So we need this 0 as a placeholder before we go on to the x term and the constant. Okay, so one little trick to doing this is whatever your degree is, you need to have one more term here than the degree. So a 4th degree means you should have 5 numbers in this first row. Okay, and then out here, you're going to put the number that you want to substitute in. Okay, now once you've set it up, here's how it works. The 4 comes down, and you start with that underneath. And then you take negative 2 times 4, and you put that answer right here, negative 8. Okay, so that's multiplying. Then you take this row and you add. So the 2 plus the negative 8 is going to be a negative 6. And then you keep doing this. So we multiply. Negative 2 times negative 6 will be positive 12. And then we add to get 12. And then we multiply. So that's going to be a negative 24. and then we add to get negative 25. And then one last time we multiply to get 50, and we add to get 57. And this number that we get here at the end, that is what f of negative 2 is going to equal, which matches what we did with direct substitution, but this is a little easier way of getting there. We don't have to worry about any of the exponents. We don't have to worry about substituting in. All we have to do is multiply and add. Okay, so why don't you try one? Okay, we can see here that this is what I just showed you. All right, so that gets us to the 57. So why don't you try one now? We've got 3 different problems here. Go ahead and set each of them up using the synthetic substitution to see if you can get the answer, and then answer your Zaption question before you continue to finish up our lesson. All right, let's check our answers quick. So these are the answers you should be getting from using your synthetic substitution for 2, -3, and -1 in each of your functions. If you're not getting those answers, pause for a moment, go back, take a look at your synthetic substitution, see if you can figure out where your mistake is. All right, that's all we're going to do for this lesson. You're going to be asked to identify polynomials, identify parts of polynomials, and to use synthetic substitution and direct substitution as a way of evaluating polynomials. That will get you through the 2.2 practice. And again, I'll be in Hanoi tomorrow, so if you have any questions, I'll be there to answer them for you. And don't forget to check your answers on Canvas when you're done. I look forward to seeing you tomorrow. Have a good day.